Welcome dear learners. We are continuing the course Quantum Chemistry. In this module, we are discussing the operator postulate of quantum mechanics. In this module, the contents are operator definition, Hermitian operators, statement of operator postulate, illustration of operator postulate, linear momentum operators, kinetic energy operators, and Hamiltonian operator. First of all, what is an operator? The definition is like this. An operator is defined as a shorthand representation of well-defined mathematical procedures to be performed in an arbitrary operand. An operand is a function on which we are operating with some operator. So every operator is a shorthand representation of mathematical procedures. Here d by dx is an operator. This is known as the differential operator. D by dx of x square, the result is equal to 2x. That means d by dx implies the fact that we are going to differentiate the operand x square with respect to x. So the indication to perform differentiation with respect to x is obtained from this shorthand notation, that is d by dx. In order to differentiate an operator from a quantity or a variable, we are placing a hat above an operator. That is, operator A is denoted as A hat. D by dx is an operator. Similarly, multiplying with the constant is denoted as K hat, is a constant operator. In certain situations, in quantum mechanics, we have to multiply some functions with the 0. Multiplying with the 0 is to annihilate or to remove a function, a mathematical function or a state function. That is, multiplying with the 0 is called null operation, and 0 hat is known as the null operator. So in quantum mechanics, there are enormous quantities of operators, and even for every physically observable quantity, there is a concerned operator in quantum mechanics. Now we are going to details of a type of operator called Hermitian operator. Actually, Hermitian is a property of operator. Some operators have Hermitian property. Some other operators having no Hermitian property are said to be non-Hermitian operators. Therefore, now we are assessing what is the condition for an operator A hat to act as a Hermitian operator. For this, I require two functions, two arbitrary functions, two arbitrary state functions, namely the first function psi I and the second function psi j, and a concerned operator, that is A hat. Now we are going to assess whether the A hat is a Hermitian operator or not. In order to assess the Hermitian property of A hat, I have to use a mathematical expression. If that mathematical expression is satisfying, then A is said to be a Hermitian operator. The mathematical condition is like this: integral psi I star A hat psi j d tau must be equal to integral psi j. I exchange the position of I and j. So the first term is psi j A hat psi I the whole star d tau, where psi I and psi j are two arbitrary state functions. If this result is valid, the operator A hat is said to be having Hermitian property, or A hat will be a Hermitian operator. Now we are assessing the condition with some more examples. For instance, if I replace psi I with psi 1 and psi j with psi 2, then I can write the expression like this: integral psi 1 with its complex conjugate psi 1 star, then the operator A hat psi 2 d2 is equal to integral, exchanging the position of psi 1 and psi 2, then psi 2 A hat psi 1 the whole star d2, psi 1 the whole star d2. This is for two functions psi 1 and psi 2. I can also repeat with two other functions, namely psi A and psi B. See, the first function is psi A, the second function is psi B. Then the Hermitian property can be represented like this: integral psi A star, that means complex conjugate of psi A, then A hat, then psi B d2 is equal to integral, exchange the position of A and B first, that is psi B, no need for the star, psi B A hat psi A the whole star d2. Finally, I can take two more functions, psi alpha and psi beta. Then like this, the condition for Hermitian nature is like this: integral, the first wave function psi alpha star A hat psi beta d2 is equal to integral psi beta A hat psi alpha the whole star d2, where psi alpha and psi beta are two arbitrary functions. So, for any two arbitrary functions, if the results are like this, we can say that A hat is said to be a Hermitian operator. Now, important features of Hermitian operator. The two important striking features of Hermitian operators are: first one, all the eigenvalues of a Hermitian operator are real. This statement we can discuss more thoroughly with the eigenfunction postulate, and we can discuss the properties of Hermitian operator in coming modules. And the second striking feature of Hermitian operator is that two eigenfunctions of a Hermitian operator with different eigenvalues are mutually orthogonal to each other. That means eigenfunctions are mutually orthogonal. We already learned about the condition for orthogonality: integral psi I star A hat psi I star psi j d2 is equal to 0. That's the condition for orthogonality. We mentioned about orthogonality, Kronecker delta, etc. in previous modules. So, these are two important features, characteristic features of Hermitian operators. I already mentioned that we can take up this matter seriously in coming modules. Now, the statement of the operator postulate. Operator postulate is the core content of the present module, and we are moving on to the statement of the operator postulate. The statement is like this: a physically observable quantity. A physically observable quantity. Physically observable quantity means a physical quantity can be represented by a linear Hermitian operator. Linear Hermitian operator. To get to the linear Hermitian operator, write the classical mechanical expression first and replace the terms Px, Py, Pz respectively by minus ih cross dou by dou x, minus ih cross dou by dou y, and minus ih cross dou by dou z respectively. So, this about the operator postulate. There will be linear Hermitian operator corresponding to every physically observable quantity in classical mechanics. We can derive it. The operator corresponding to physical quantity can be derived by using the classical mechanical expression. Write the classical mechanical expression and we have to make the substitutions Px, Py and Pz respectively with these three quantities. This we can illustrate in the coming slides. Now, illustration of operator postulate. Let us take kinetic energy as a representative example to write the linear Hermitian operator. As per the operator postulate, for kinetic energy also, there will be a linear Hermitian operator. Let the quantity under our consideration is kinetic energy along x direction. Kinetic energy along x direction. We have kinetic energy general expression equal to half mv square. If the body is moving along x direction, the kinetic energy is marked as Kex. Kex equal to half mvx square. This is the expression for kinetic energy along x direction. To get a linear Hermitian operator corresponding to kinetic energy, I have to begin from this classical equation and replace the terms Px, Py and Pz respectively by minus ih cross dou by dou x, dou by dou y and dou by dou z respectively. Since it contains only variable x, there is a possibility for occurring Px. Then what is Px? Px represents momentum along x direction. We know momentum P is a product of mass and velocity. Therefore, Px equal to mass into velocity along x direction. In this expression, there is no direct Px is observed. So, I have to correct this kinetic energy expression to get Px in that equation. So, I can correct it like this. Kinetic energy along x direction is equal to half mvx square. In the denominator and numerator, I am multiplying with the m. So, 1 by 2m. So, numerator changed it to m square vx square. This can be corrected as 1 by 2m into mvx the whole square. You know the fact that mvx is equal to px. Therefore, 1 by 2m px square. This is kinetic energy along x direction. This is the correct classical expression for kinetic energy along x direction. Now, we have to get the linear Hermitian operator corresponding to kinetic energy along x direction. To get to the operator, what I have to do? Replace the term Px with minus ih cross dou by dou x. Then we will get the operator corresponding to kinetic energy along x direction. So, if I replace Px with this quantity, I will get the kinetic energy operator. Then, if replacement is performing, Kex should be replaced as Kex hat. That means we get an operator. Kex hat is equal to 1 by 2m. Instead of Px, I have to make minus ih cross dou by dou x the whole square. That is, the kinetic energy operator can be like this, 1 by 2m into minus is there. Minus square is a positive, minus 1 square is a positive quantity. But you know I is equal to root of minus 1. Therefore, I square is equal to minus 1. So, for taking square of each terms inside the bracket, minus minus will change it as plus. I square is again a minus. So, minus s cross square dou square by dou x square. On proper rearrangement, I will get the kinetic energy along x direction operator as minus s cross square by 2m minus s cross square by 2m dou square by dou x square. It should be noted that there is always a valency for every operator where we are putting the operand. So, the kinetic energy along x direction can be represented as a linear Hermitian operator. That linear Hermitian operator corresponding to kinetic energy along x direction is given by minus s cross square by 2m dou square by dou x square. This is illustration of the operator postulate. Now, we can move on to all kind of kinetic energy operators. There are actually 4 type of kinetic energy operators. First one, KEX hat, that we already discussed, kinetic energy along x direction operator, kinetic energy along y direction, kinetic energy operator along z direction, and finally total kinetic energy operator. Total kinetic energy operator. Out of this we derived the operator corresponding to KEX, that is kinetic energy along x direction. We know KEX hat is equal to minus s cross square by 2m dou square by dou x square. By adopting similar procedure, we can also derive expression for KEY. How we can move? KEY is equal to half mvy square, where vy represents velocity along y direction. That is, KEY can be corrected as 1 by 2m mvy the whole square by multiplying numerator and denominator by m. And we know mvy is equal to py, that is momentum along y direction. Therefore, kinetic energy along y direction is equal to 1 by 2m py the whole square. This is the classical mechanical expression for kinetic energy along y direction. Now, to get to the operator corresponding to kinetic energy along y direction, I have to replace py with the minus ih cross dou by dou y. Therefore, the kinetic energy operator along y direction can be obtained like this: 1 by 2m into minus ih cross dou by dou y the whole square. That will lead to the ultimate result minus s cross square by 2m dou square by dou y square. By proceeding through a similar method, we can also get expression for KEZ. That is, KEZ will be equal to, KEZ hat will be equal to minus s cross square by 2m dou square by dou z square. Dou square by dou z square. So we have KEX hat, KEY hat, and KEZ hat. And finally, there will be one more operator, that is the total kinetic energy operator. Kinetic energy is an additive property. KE total is equal to KEX plus KEY plus KEZ. Similarly, operator can also be clubbed to get the total kinetic energy operator. So, total kinetic energy operator also follows this relation. That is, total kinetic energy operator KE total is equal to KEX hat, KEY hat plus KEZ hat. On adding these three, KEX hat, KEY hat and KEZ hat, there are 3 expressions to be added. In all the 3 expressions, there is a common term minus s cross square by 2m, minus s cross square by 2m, etc. Minus s cross square by 2m, so on so on. So, I am taking the sum minus s cross square by 2m as a common factor can be taken outside. Then dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is an operator we already learned in the previous modules, that is called Laplacian operator or Laplace's operator. Therefore, total kinetic energy operator Ke total hat equal to minus s cross square by 2m. This is equal to del square. This is a very, very important information. Total kinetic energy operator equal to minus s cross square by 2m del square. That all about the discussion on various kinetic energy operators. Now, the total kinetic energy operator, for the sake of convenience, Ke total. Once again, Ke total hat equal to minus s cross square by 2m del square. If we add potential energy with this, we will get total energy. Total energy operator, that is called Hamiltonian operator, that we can discuss in the coming slides. Now, linear momentum operator. These are very important in quantum mechanics. As far as energy and momentum is concerned, these two are very important properties. Now we are discussing linear momentum operator. Let us consider a body of mass m moving with a velocity v. Then the mathematical expression for momentum is P is equal to mv. It should be noted that momentum can be along x direction, y direction or z direction. So there are three linear momentum components. They are nothing but Px simply equal to mvx, Py known as mvy and Pz, that is mvz. So if I wish to write Px hat, I have to replace mvx by minus ih cross dou by dou x. This is a very important relation. Similarly, mvy should be replaced by, or py should be replaced by minus ih cross dou by dou z to get the py operator or momentum along y direction operator. That is py equal to minus ih cross dou by dou y. Similarly, the momentum operator, the linear momentum operator, corresponds to z direction. That can be represented as Pz hat is equal to minus ih cross dou by dou z. So, Px hat, Py hat and Pz hat are three important linear momentum operators which corresponds to momentum along x direction, y direction and z direction. Now, square linear momentum operators. We already learned about Px hat, Py hat and Pz hat. They are the linear momentum operators along x, y and z direction. Now we are going to derive expression for square linear momentum operators. That is, we have to get expression for Px square hat, Py square hat and Pz square hat. How to get that expression? In order to get that expression, we know Px square equal to mvx the whole square. Mvx or Px to get to the operator, mvx or Px should be replaced by minus ih cross dou by dou x like that. That is Px square hat equal to mvx or Px should be replaced by minus ih cross dou by dou x minus is cross dou by dou x the whole square. Minus ih cross dou by dou x the whole square. That is Px square hat. Px square hat equal to minus minus is positive I square is again minus sign. So, minus s cross square dou square by dou x square is px square hat. Similarly, we can also derive py square hat, that is equal to mvy the whole square, mvy the whole square. To get py square hat, mvy should be replaced as minus ih cross dou by dou y the whole square. This leads to the result minus s cross square into dou square by dou y square. This is py square hat. Finally, on similar argument, we can also get expression for pz square hat. Pz square hat will be equal to minus s cross square dou square by dou z square. So, these are three square linear momentum operators. Now, we are moving on to Hamiltonian operator. I already mentioned the Hamiltonian operator. Hamiltonian operator is represented as H hat. H hat is the total energy operator. Total energy is the sum of two kinds of energy. That is the kinetic energy and the potential energy. So, total energy operator comprised of total kinetic energy operator and potential energy operator. And H hat equal to Ke hat plus V hat, where V hat represents the potential energy. Since the potential energy is a fixed quantity, it is as such represented as V. But we know Ke hat or Ke total hat is equal to minus s cross square by 2m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square, or simply minus s cross square by 2m del square, where del square is called the Laplace's operator. This corresponds to total kinetic energy. I have to substitute this value here in the expression for Hamiltonian operator to get the final expression for H hat. That is, H hat or Hamiltonian operator equal to minus s cross square by 2m del square plus V, where V represents the potential energy and this term represents the kinetic energy. So, the Hamiltonian operator is the total energy operator associated with a system. We are familiarized about the Schrodinger wave equation, especially time independent Schrodinger wave equation, as H hat psi is equal to energy into psi. There H hat is called the Hamiltonian operator, or H hat is equal to minus s cross square by 2m del square plus V. Now, the two important operators which are very significant in quantum mechanics, they are the time and energy operators. First of all, the time operator, that corresponds to the quantity time. Time operator is denoted as T hat. The time operation is simply multiplying by time. That is, T hat of f of x equal to T into f of x. That is, if we are seeing T hat, that implies we have to multiply with the T. The other operator is energy operator. The energy operator, not total energy, but the energy operator with reference to time is denoted as E hat. The energy operator is IH cross dou by dou T. That is, E hat is equal to IH cross dou by dou T. E hat is equal to IH cross dou by dou T. Thus, what is meant by energy operation? In energy operation, you have to multiply with IH cross and also to take first differential with respect to time. So, the energy operation implies taking derivative with respect to time and also multiplying with the IH cross. So in energy operation, we have to perform two things on the operand. First of all, the operand to be differentiated with respect to time, first order differentiation, followed by multiplication with constant, that is IS cross. Thus, in this module, we have discussed various kind of operators, Hermitian property, Hamiltonian operator, and commuting property of operators. Several properties we have discussed yet, and these are very important operators which are commonly used in quantum mechanics. They are X or X hat, which represents position of the body along X direction. Similarly, Y hat and Z hat represents position along Y and Z axis. Px stands for momentum along X axis. Similarly, Py and Pz are also there. X square is the square of the position operator. Px square is the square of the momentum operator. And also the last two, the time operator and energy operator. I already mentioned about energy operator. Energy operator is a very important quantity. That is E hat is equal to IH cross dou by dou t. Therefore, energy operation on an operand is first differentiation with respect to time followed by multiplication with the IH cross. Thus, we have discussed the operator postulate and various operators. That all about this module. Thank you.